because it'll show you sort of my thought process of something I've never done before. And I tend to go slower when it's one I haven't done before, right? Okay, so what's the maximum compression in the beam? I've got this wooden beam here supporting this wire, and I want to know what the maximum mass is on here in kilograms. So it's a little bit different than what you're sort of used to. Maximum mass that I can put on there. There's a strut here holding this wire, and the wire is
maximum force.
well. It says what? It says
Oh, we want maximum.
what's the maximum force? So I got maximum compression. Same thing, right? It's a compression force. Okay, so that force is directed at an angle. If you, I'm going to draw
Does it say max?
max compression. How about, can I just label it, like, regardless of whether it's tension or compression, it's a force, right? Okay, so how about I label it in red? I'm going to call it force, and I'm going to draw in these other components here. And how would you label, this would be F what? What would you call that?
X.
Fx maybe, sideways, and label this one Fy? Does that work for you?
Yeah. So we're looking for the beam that's on an angle.
Yeah, I'm looking for how much force in here in this hypotenuse.
Okay.
Okay, so if the maximum compression, no, actually, sorry, I'm not looking for that. I'm telling you that the maximum is 2,500 before it will crumple.
On F.
The maximum force in here, so what I'm saying is that is 2,500, right? And we really want to know what value of M can I put on there. So if I want to know what value of M, how am I going to get M? Like what formula is going to be my last one, do you think? Is it accelerating? No? Yeah, I think so, right? I'm thinking the last, I was thinking about this the other day. I'm going to give you a bit of a new technique. Work backwards kind of, right? So the last thing I'm going to do is FW equals mg. I know G, solving for M, so I need FW. How can I get FW out of this?
Well, can you get Fn from W?
Yeah.
If it's something sitting on a flat surface, but that's not this situation, is it? How do I get FW? What's FW equivalent to here? FD would be like on a ramp kind of thing, right? T? Yeah. Well, but which? Is it this one, or this one, or this one?
Why?
Fy. Is Fy not equal to Fw? Is it not, right? Because there's no vertical acceleration. This force right here must be balanced by this one. Right? Can I get Fy out of this triangle here?
Yeah.
Sure, right? Would that triangle be the same? Like, could I just draw it like this too? Would it be, like, is that the same Fx? Is that the same Fy? Sure. So you could deal with this 60 and this 2,500 and this Fy. Or if you wanted to deal with this Fy over here, instead of 60, you'd have to use 30 degrees, right? Is that going to change anything? Well, no, because here the Fy is opposite, so it'd be sine 30. Here the Fy is adjacent. Did you know that the cosine of 60 is the same as the sine of 60? Or sine of 30? Did you know that? Okay, so it really doesn't matter here, right? So I'm going to get my Fy. How am I going to get my Fy? I'm going to use something like sine 30 is Fy over F, right? That's my backwards solution path.
You're doing 30?
Doesn't matter. Do you want to do 60?
Because
Okay, you do 60 and see if you get the same thing. So that's my path. So I'm going to do this one first, right? So I'm going to write
what is the Fy over left?
Fy over F
Oh.
in the triangle. I'm going to write sine 30 is Fy over F. So Fy is equal to 2,500 times sine of 30. 1,250. Well, I guess I don't need to do that. FW equals FY, so like, is this all there is to it?
Yeah.
Oh,
For
see.
example.
Let's see.
It's a poor example.
Well, we don't really do, we're not gonna have a question this season.
Is this an easy one?
Yeah.
Well, yeah, now you've seen it.
It took some, yeah. There's a we never dealt with the compression though.
Yeah.
Thinker, but there was really no steps.
Tissues are up there.
Stick it.
I'm saying that it was easy.
I know.
It's not the same.
What am I saying, Jason? Explain it to him.
No.
Well, I don't know, you said it was a thinker, but it was easy.
Yeah, and I said tissues are up there.
It's not the same when you use sin 60.
I love how the look on his face and he's laughing.
I don't know what you're talking.
Explain it to him, Jason.
It's not the same answer when you use sin 60.
Well, I get that, but why would I try to look at it? It's easier.
It's not the same answer.
What?
You use sin 60.
No, not sine 60, cosine 60. It's adjacent, cosine 60.
What?
Adjacent, FY is adjacent to 60, cosine 60. You want to do a different one like that, Steve?
I don't know.
Now you're just worried I'm going to make fun of you, right?
Is there one where like it was like it's more of a
I know one that's hard. Actually, I'm going to get you to try it first.
alright.
Let me find it. I know one that's harder. Page 237, number 4. This is actually a really good one. 237, number 4. Oh, you want to see that? Sorry. 237, number 4.
Are you allowing us to do it?
Do you want to try it first? Okay, you guys try it. Here's a well. I'll draw it. I did bring this up yesterday because I was worried that we might not get to this question, but now we're going to get to it. I'm not too worried. Okay, so you got this well, you got a 4-kilogram pail of water, and these are like wooden beams here, right? And that height is 1.9 meters, and the distance across is 1.3.
1.9.
1.9, yes. 1.9 in height, 1.3 across. And the question says, how much compression force is exerted on each beam by the water pail? So you're looking for big F, the force inside that wooden beam. I'll let you think for a minute or two. Okay, what's the first thing should we try this backwards thing? Let's try the backwards thing. I want to try it. No? You don't like that, Steve?
No, I think we should do it.
Oh. Try the backwards thing. Okay, so I'm trying to find that force, right? Okay, so I'm going to need an angle here, aren't I, right? Like I need, what do you want, that angle? Do you want this one down here? Which one do you want?
Well, we're just looking for like the hypotenuse of that triangle split in half, right?
Basically.
So, do you actually need an angle? Because you have two measurements. You have 1.9 and 0.65.
So?
So can't you just do?
Oh, if I take the 1.3 divided by 2, that's only going to give me that distance,
Okay.
isn't it? Like those are meters. So if I do that, that's going to give me that distance, is it not? Like, that's a good thought, but it's just the distance, right? I need to know that force. Do we all agree we're going to need that angle? The only way to get the angle, what they did was they gave you the angle, but they gave it to you in the height and the distance across, right? That's how they gave it to you.
So what do you mean by doing backwards?
Well, like what do we have to find out? What's the last thing we're going to find out? Like we did it over here, right?
Because I read it backwards and I don't know.
Well, you write it backwards and then you just follow that plan forwards. Retrace your steps. I don't care. I don't have to do it backwards. Okay, let's agree we got to find the angle first. Okay, so I'm going to redraw this. This is 1.9. That should be straight up and down. Yeah, what's this distance here?
Which angle or do we want?
D- Well, again, does it matter whether it's this one down here or this one up here?
No.
Doesn't matter, right? We're just going to use sine in one and cos in the other, right? So, Jimmy crack corn, man. 1.3, is that what this is? 0.65, right? Divided by 2? I don't know why, but I'm going to pick this angle down here. So I've got opposite and adjacent, so I'm going to use theta equals inverse tan, opposite over adjacent, 1.9 over 0.65. I get 71 degrees down there. Is that what you got? Okay, so 71 degrees. So now, in this triangle here, I'm going to redraw it, but I'm going to draw it with this is distances. I'm going to draw this with forces. So this is the weight force. And really what I'm trying to find, you know what, you guys? This is just as easy as the last question, isn't it? No? Because what is the weight force? 4 times 9.8, which is 39.2.
So we just redo it, but using
So
this instead of distances?
this value in here, is that angle still the same?
Should be.
Yeah, the angle's the same, right? So, but this FW here is the shared thing, right? So this value right here is actually equal to, you know what, let's not call it FW, let's call it FY, shall we? Well, it's the Y component of that compression in the force. So Fy is 39.2 divided by 2.
Why are you dividing it by 2?
Because there's this beam on this side. This beam covers half the 4 kilograms. This beam covers the other half of the 4 kilograms.
No, I won't have to see this.
19.6. And now it's just opposite, hypotenuse, sine, right? Sine of 71 degrees is my opposite, my Fy, divided by my F. Fy is 19.6. F is equal to 19.6 divided by the sine of 71. .7. Can someone look in the back and see if we got it right?
I don't know how to use that.
You don't know how to use it. Okay, well, there are 2 sets of answers in the back.
Yeah.
This is applying the concept. See that little circle on the right-hand side?
No.
It says applying the concepts there. So at the back, there's 2 sets of answers. There's ones that are numerical answers to applying the concepts. That's where you look. So this is section 7.3. 7.3 number 4. It says 20.7. Perfect. Part B says, what outward force do the 2 beams exert on the well's wall? So what are they talking about there?
I don't know.
What's the force?
They're talking about this sideways push, right? Which is really just fancy talk for the X component, is it not? That's all it is. So cosine 71, we got our hypotenuse there, right?
What are we looking for here?
It said how much outward force do the beams push on the well's walls, right, in part B?
Okay, so what are we looking for then?
The question asks, What outward force do the two beams exert on the well's wall? So it's really just fancy talk, Steve, for Fx, isn't it? Like how much push is there sideways out? So it's just Fx. I got cosine 71. Adjacent is my
So
Fx.
do you not think outside the walls be vertical, like at the outside wall,
No, but it's
like this?
how much force, what outward force do the two beams exert on the well's wall? Outward, to the out, sideways. So cos 7 is equal to Fx over hypotenuse F. Fx is going to be F cos 71. 20.7 cos 71. $6.7. Anyone got that marked in the back of the book?
That's right.
Yeah? I got 1.3 times 10. No, that's not right. 6.71. There we go. Perfect. Oh. 4C is a bit of a thinker. What additional vertical compression is exerted on the bricks under the beams? What additional vertical compression? How much force do the bricks sense? It's not 19.6.
That is.
Is that what it says in the back? Really?
Well,
Is that what, really, that's what it says?
Yeah, it
Oh, they're stupid.
is.
What additional vertical compression? It doesn't say 19. Oh. I disagree.
Oh. All right.
Why do you think I disagree? It'll be a little bit more than 19.6, I Because there's also the weight of the beams, right? That's what I thought they were getting at. The weight of the beams, right?
I never told somebody.
No, they never told me. Well, that's why it says what additional, right? That's why I thought they just say the mass of beams. Okay. You wanted me to do another one, Steve, though, right? You wanted me to do,
I go to the washroom first.
yeah, but remind me what, oh, you wanted me to do one where there was a vertical component in a force.
Right.
I found one too. Let me see if I can find it again. Jason has asked for question number 11 on that sheet that I gave you the day I was away, Tuesday, I think, right? That has the scary looking font there, equilibrium applications of Newton's laws of motion. So there's a kite. It weighs 0.6 kilograms. The string makes a 55-degree angle, and the tension in the string is 35 newtons. Okay? This is number 11 on that sheet you got on Tuesday. And the question is, what determine the force, the magnitude and direction that the wind exerts on the kite? Riley, what's the what's the acceleration of the kite? John, is your hand up to answer there, or are you just making a motorbike sort of gesture? What's the acceleration of the kite? It's easy. 0, yeah, it's 0, right? It's not going anywhere. So what does that mean then? It means the net force is also 0. So that means that if there's 35 newtons at 55 degrees down like this, that has to be balanced by 35 kind of up at another angle, right? Now that would be entirely true, except there's one problem. The kite has a mass. So you can't say that this 35 newtons down at that angle is the only force acting on the object, because there's also, right? Could you look at this as an equilibrium question? Here we have a tension. here we have a weight force, and the equilibrant is something like this, which is, I was going to put FW, but that's not very good. Force wind, but that's not a very good one, right? How about I say FA? Would you agree that the FA and the FW and the tension have to add up to 0?
Yes.
Because the thing, what's the net acceleration, Riley? 0. It's not moving, which makes the net force 0, right? The sum of all of those forces is 0.
So if the acceleration is 0, the net force has to be 0?
Yep,
All the time?
all the time.
So that means Fn equals Fn equals Fn.
Say again? Well, I'm just thinking here. I haven't gotten to a formula yet, right? I mean, really, I guess if you want to say, you could say that F net, vector F net, is equal to vector FW plus vector F applied, which is our wind force, plus vector T, which is our tension in the string.
Must you put all those vectors in there?
Well, I'm just emphasizing the fact that this is a vector thing. Really, what I'm saying is this guy here is the equilibrant of those two. An equilibrant simply means opposite of resultant. So aren't I just saying here, add those two together and find the resultant and then do what? Flip it? Isn't that kind of what it boils down to? So how do I add those two guys? Hey, this is just vector addition, isn't it? This is just vector addition. That's all this is. So FW is straight down. FWX, 0. FWY, weight force Y, well, there is only one. It's equal to mass times gravity, right? I don't think I've ever done this question. That's the good thing about concussions. There's lots of new experiences. You don't remember things. I get 5.88 newtons. It's the mass of the kite times gravity, right?
How did you know it was a vector addition motion?
Well, I sort of worked it through. I sort of had to just think it through.
But how?
I tried to verbalize my thought process there.
Yeah,
How did you didn't get it? Should I go through that again?
I don't know how you found it.
Well, it's not just, I can't give you like a one-word answer. I got to sort of, right? I looked at this and I realized that this kite was not moving,
Yeah.
which means the acceleration is 0, which means the net force is 0. And when I get a net force of 0, then that implies, that leads me to think, okay, what forces are acting on it that add up to 0? Well, those forces are, and I got thinking, okay, I got a tension force, I got this wind force that they want me to find. Are there any other forces? Yes, there is. There's a weight force.
I haven't taken over tension.
It told me in the question that there's a string attached. Well, it says there's a tension in the string.
Oh, okay.
Is that a good enough answer? I don't know if I can give you a better one. Tension is like this, right? So I need a tension X and a tension Y. So 55, tension X is cosine adjacent, so that's going to be 35 cos 55. I sure hope I get this right, because I'll look stupid if I don't. And I don't need any help looking stupid. 20.1. Yeah, 20.1.
Oh, for that one.
That's TX, right? So TY, tension Y, is going to be 35 sine 55. $28.6. No, 28.7. What's the big idea here? I'm going to be adding these together to find the resultant and then doing what? Flipping them. That's what I'm doing. We keep coming back to this vector addition over and over again, don't we?
I thought you needed the FA or whatever.
I do, but it's the FA is the equilibrant in this case, right? So I'm going to find the resultant of those two, and then I'm going to flip it. So Rx is going to be 0 plus 20.1, which is 20.1. Resultant y is going to be those two things added together.
Wouldn't it be negative 20?
No, I'm adding them.
But no, it's going to the left though. Your arrows are pointing left.
Oh, yeah, right.
But then when you split it, it'll become positive.
Yeah, well, but no, let's do it right. Hannah's right. That should be negative, and in fact, this should be negative, shouldn't it? And so should that. You're right. Because they're to the left and down. She's right. Minus 34.58. Can I write this statement? Since the applied force is the equilibrant in this case, right? I'm just going to take that x and that y and flip those, right? So I'm going to say FAX is going to be plus 20.1, and FAY is going to be plus 34.58. The wind, we know the wind is up and to the right. To the right and up. Oh, that doesn't look good. This calculator, the sticky buttons. Ah. 39, it's basically 40 newtons, right? And that angle there. This is a good question. No, I wish I'd seen this one before. I better change it. I'm not going to give you a question exactly like one. So this would be 40 newtons at, I guess it would be 60 degrees above the horizontal, right? 60 degrees ATH above the horizontal. What's the answer? 40 newtons at 59.8 above horizontal. Is it a good feeling when you can do something like that? Do you feel that sense of satisfaction when you get the answer right like that? I do.
So how do you know to do that whole like above horizontal, below horizontal, whatever?
Well, here my force is, I don't have a north or south, right? So I got to have some way to describe it.
Okay, so you just.
So, and in the question it said 55 degrees above horizontal. So they described this as 55 degrees above horizontal. So that's 60 degrees above horizontal. That's a really good question. Yeah.
Sorry about the paper.